Good morning, dear student. Let us start the second part of the module 3, that is a time response of feedback control system of second order system. We have already discussed the effect of location of poles and zeros on the transient response of first order system. We have seen all possible conditions and we have seen how poles and poles will get affected, and if we add zero, how response will get affected. If we add a delay element, how a response will be the response will change. And by changing the capital K, that is DC gain of the system, and by changing the capital T, that is a time constant of the system, how response was changing. All those things we have studied for the first order. We found that if the mathematical model is available, then it is very easy for us to find the time response. Otherwise, finding a transfer function itself is a tedious job. We have to do that. Then we have to find it time response. Okay. So, compared to the first order, second order system exhibit a wide variety of, response graph. The response graphs will be, you will find different what we call shapes, different patterns. And unlike the first order, what we found, we had a capital T and capital K parameters we were changing, and we found that the offset and the speed of the response was changing. But here in the second order, it is not like that. You will see that once the parameter changes, you will see that there will be a wide range of responses possible. So we have to analyze and we have to describe that. Okay. As we have found that change in parameters of the second order system can change the form of response. Okay. So we see that the second order system can display characteristics much like first order system, or depending on the component values, we will find that a system can completely oscillate, and for its transient, and we can completely die out the oscillations completely. It all depends on the system parameter. What we decide, we can have a suitable response or desired response, we can have it with a suitable design of the system parameters. So generalized second order system, how it looks like. Okay, we have here to the right a block diagram. Okay, a closed loop second order control system we have. Okay, the forward path or open loop transfer function, we have omega n square divided by s into s plus 2 zeta omega n. Okay, and if you have a unity feedback, then the final transfer function will be C of s divided by R of s, which is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. This is what we call it as the standard second order system transfer function. What is omega n in this transfer function? Omega n is an undamped natural frequency of second order system, which is the frequency of oscillation of the system without damping. Okay, every system is having an ability to oscillate. If there is no damping present, what is that maximum frequency at which it can oscillate is given by this omega n. We have zeta, we call it as damping ratio of the second order system, which is the measure of the degree of resistance to the change in the system output. Okay, so these two are the major parameter which will decide the response of the second order system. So we have here for one example, we have been given a transfer function. We have to find out undamped natural frequency and the damping ratio. Okay, so if the transfer function is given, we have to take up the denominator polynomial of the transfer function, which is actually the characteristic equation. We have to compare that with the standard form of the characteristic equation, and we have to find out the two unknowns or two things which has been asked. So that's what we are doing. We are comparing the denominator to the standard characteristic equation. Okay, so you can compare numerator also here, because omega n square what we had in the numerator, denominator also we have to the last term as omega n square. So we say that you can compare both numerator and denominator, but denominator polynomial is what we have, the characteristic equation that alone will give you omega n and zeta value. Okay, so comparing the standard transfer function with the given transfer function, we have omega n square as 4. So that implies what is omega n? 2 radians per second. And again, I'll take the coefficient of s equating to the coefficient of s of the given transfer function. And I can see that the zeta is equal to 0.5. Okay, so just equating the coefficient of s and equating omega n value, you will get this omega n and the zeta value. Okay, so now we will take this transfer function and we will try to find the roots, because second order system, right, we will be having two poles. We'll be having two poles existing. Based on these two poles, or you can call it as roots of the characteristic equation, these two roots positions will decide the pattern of the response. Okay, these two roots position and zeta and omega n value together will gives us the pattern. What is the output CFT pattern will look like. Okay, so now the two roots we can have it this way. In the previous slide we have this, because this is a quadratic equation, that is the characteristic equation or the system characteristic equation. It's a quadratic equation. According to the quadratic equation roots, we have minus b plus or minus b square minus 4ac, square root of b square minus 4ac. What we have that formula, we will just apply that formula. We got the two roots here. Okay, so the two roots will decide along with the zeta value, will be having a different patterns possible. We will see one by one. Okay, so according to the damping ratio zeta, second order system can be can be divided into four categories. Okay, so based on the zeta value. So first we will see what is overdamped condition. Overdamped condition is defined as when the system is having two distinct real poles and it is having a value, that is zeta is having a value greater than 1. Okay, what is an overdamped condition? Overdamped condition is a condition where zeta is becoming greater than 1. Okay, when zeta becomes greater than 1, according to the two roots what I have here, these two roots will become the real and distinct. Okay, you can see the plot here. This is an S plane. Horizontal line is a real axis, vertical is an imaginary axis, and you will see that at minus a and minus b you will find two real roots, distinct roots exist for this condition. Now I'll go to the next condition where we have underdamped situation, where your zeta will be less than 1 and greater than 0. Okay, between 0 to 1 you have zeta value. In this reason you will find that the system is having two complex conjugate poles. Okay, so it looks something like this. Okay, so it is symmetric about the real axis, the roots, you have what you will get. Okay, because it is a complex conjugate poles, so it has to be symmetric. So this is how the roots look like. Okay, underdamped condition. Next is undamped condition. That is for zeta is equal to 0, we have an undamped condition. Undamped means what? Your system will be oscillating to its maximum frequency possible. So there is no damping exist, but ideally we say that this situation will never exist. Undamped situation will not exist because you cannot design a second order system having zeta 0. Very tough. Whichever component, physical component contributing to the second order system will be definitely having some part of damping. So you cannot have a damping free system design possible. So we usually say that undamped system doesn't exist practically. Anyway, we can have a case like undamped with having a zeta 0. Then what is actually happening? That is when the system has two imaginary poles, lying on, it's lying on the imaginary axis. Okay, it is having two imaginary poles. That means the roots doesn't have a real part. Just you can go through the two roots which I have mentioned here. The first root you make zeta 0. Okay, second root you will make zeta 0. Then what you will get? You will get, you will get plus or minus j omega n as the roots. Okay, by making zeta 0. So you will get, poles lying on the imaginary axis. So this is a marginally stable condition, what we call it as. Whereas previous two cases, it is stable condition actually. Why do I declare as a system stable? Because whenever we find poles to the left half of the S plane, I repeat, the roots, characteristic equation roots, if lies on the left half of the S plane, then the system is stable. Overdamped condition, system is stable. Underdamped condition, system is stable because the roots are lying to the left half of the S plane. Okay, and we have the third category, that is undamped condition, where roots lying on the imaginary axis, it is marginally stable. Okay, if one more pole lies on the axis, then it will enter to unstable condition. Okay, so we call it as, marginally stable condition, marginally stable situation, because we have two poles on the imaginary axis. For zeta is equal to 0, undamped condition. We have lastly the critically damped condition, when the system has two real but equal roots, equal poles. That is, for zeta is equal to 0, you will be having, omega n, plus or minus omega n, or what we call it as the roots. You substitute zeta is equal to 1, you will get that, it is omega n, we minus omega n we have. So both the poles will be having same value, minus omega n. You can see here S1 and S2, the two roots, if I call the first root as S1, second root as an S2, then you can say that, it lies on the minus omega n value. So say for example it is point A, you will see that both the poles lies on the same point. So system has two real but equal poles we have, and system we will find stable because we have roots to the left half of the S plane. Okay, so next topic what we have is time domain specification. Okay, the response what we draw for the second order system, to understand this specification, to understand this response, we should know few terminologies or few specifications. Okay, through these specifications we'll express the second order system response actually. So here we have taken one unique condition, one specific conditions we have taken, that is underdamped condition. Okay, this is usually occurring situation, we can call it as. So, and we always prefer to operate in this zone, that is zeta between 0 and 1, and always omega n greater than 0. This is normally expected situation. So we are going to analyze the time domain specification for this particular condition. Okay, so overdamped we can have it, only thing is, you will find rise time slow. Okay, critically damped, very difficult to design, and undamped doesn't exist. So usually we found that, this is most occurring situation. So we have here a zeta between 0 and 1, omega is greater than 0 condition we have taken. A second order system is plotted here for a unit step input, looks like this. Okay, you can see here the graph. Okay, output rising here, rises, reaches the input, and it overshoots, comes down. You could see the oscillations here. Okay, and again it again overshoots, but with a little less height, and again it's coming down, again overshoots. It will settle down at some point. Okay, so this is what the response of a second order system under damped condition. So now we define few, parameters here. Okay, you can see TR, TP, TS, TD, MP, and settling time, allowable tolerance. We will see all these things one by one. So to start with the delay time. What is a delay time? Delay time is the time required for the response to reach 50% of its value. 50% of its final value. Okay, so we say that the value is what the input applied is 1, so we are expecting 1 as an output, that is level 1 or value 1 we are expecting as an output. So the response, that is time taken by the response to reach the 50% of its final value. This is what the final value we are expecting our system to take. So 50%, that is 0.5. That is what we call it as a delay time. Okay. Next is we have a rise time. Okay, rise time. What is a rise time? So rise time we define different for different zeta condition. What is the zeta condition we have here in this graph? In this response curve, we have zeta 0 to 1, that is underdamped condition we are talking about. For this particular condition, we say that rise time is the time taken by the output response to reach the input for the first time. You can see that it is reaching the input for the first time. Okay, it is reaching here for the second time. This we don't read it. It is reaching input for the third time, so on. But output reaching the input for the first time is what the rise time we are talking about. It is crossing the input line. That intersection or the time at which the output reaches the input point is called the rise time. So this is the definition of rise time we give it for the underdamped condition. For an overdamped condition, what we do it, in an overdamped condition, your output will never cross the input. So I cannot have 100% possible because output will not reach the input. Okay. So we say that that time for, overdamped condition, it is 10 to 90%. 10 to 90% rise, we will consider as a rise time. That is output reaching from 10% to 90% is what the rise time we define. Okay, similarly we have critically damp. Okay, so critically damp, it is 5% to 95%. Okay, for a critically damped condition. For a for an undamped, we don't have any TR existing. So undamped means we'll be having oscillations. For that we don't have any time specifications exist, so there we don't have a rise time into the picture. Okay, so this is about the rise time. We have rise time different for the three cases. For undamped, we don't find rise time existing. So for the other three, we have rise time calculated in a different way. For an underdamped, it is 0 to 10. For overdamped, it is 10 to 90% rise in the output is what the rise time. And in the critical damping, it is 5 to 95%. Next, we have what we call NP, that is maximum overshoot. What we call it as a peak, peak time. That is maximum overshoot happening. Corresponding time we call it as a peak time. We will try to see what is that TP, that is peak time. The peak time is the time required for the response to reach the first peak of the overshoot. This is what we have, the highest peak, that is the first peak. So time taken by the system to reach this first peak is what we call it as TP, that is the peak time. Okay, peak time we call it as. Similarly, we define an overshoot MP. This is a height we have from input level to the first peak. This is what we have MP. So usually we MP, that is overshoot. What is overshoot? That is the maximum overshoot is the maximum peak value of the response curve measured from the unity. If the final steady state value of the response differs from the unity, then it is common to use the maximum percent overshoot. It is defined as the following. We have defined here. Okay, it is C of TP minus C of infinity divided by C of infinity. What is C of TP? This is the output value or the highest value or the value at the peak time. Okay, it's the output value at the peak time minus output value at infinity, that is at steady state. What is the maximum value we have at steady state divided by the steady state into 100%. So why do we always go for a maximum percent overshoot instead of only the maximum overshoot? Is sometimes the response differ from the unity. Okay, final steady state value response will be differ from the unity, so I cannot take the overshoot calculation from the unity level. So always we give that in percentage. Okay, we give that overshoot always in percentage. Okay, next, what is the settling time? Settling time TS, you can see in the graph we have taken somewhere here. We have drawn the two lines, that is what we call it as allowable tolerance. The tolerance you can fix. tolerance you can fix to 2%, tolerance you can fix 5%. So 2% tolerance means what? Only 2% variation from the applied input, we can wait and we can get. Whereas 5% means you can take the 5% tolerance. Okay, so 5% tolerance you will be reaching early. 2% tolerance takes time. Okay, always 2% tolerance takes time. That is settling to 2%. We have to wait longer. So usually we go for a 5% tolerance. So I have here a margin drawn for the 5%, and I have just taken here the time, corresponding time at which output is reaching to 5% tolerance band. Okay, that is what the time we are calculating. We call this as settling time, TS. Okay, so this is what we have it as a settling time. It always depends on what percentage of settling value you are talking about. Settling value you can calculate for 2% tolerance or a 5%. Based on that, your TS will change. Okay, so now we will see what is how this omega n can be visualized in the pole zero plot. Okay, so we have here a pole zero plot. So let us draw the let us visualize this omega n in the pole zero plot. So how to do it here? You take an S-plane, locate the pole first. So pole you have to join, that is pole and the origin of the S-plane you have to join. That radial length what we get is what we call it as omega n. Okay, I repeat, the radial length what we get is we call it as omega n. Okay, so I can say that if I draw a circle with this radial length, then whatever poles appears on the circumference of the circumference of the circle will be having same omega n value. Okay, that is the natural frequency, undamped natural frequency of the system will be same for all the poles which lie on the circumference of this circle. Okay, so like that, the entire S-plane I can divide into different concentric circles. Okay, like this I can divide entire S-plane into different concentric circles. Okay, you can imagine different circles exist like this, so that you can see that if pole exists here, you can just read the corresponding omega n easily. Similarly, there is a pole existing here, say for example, I can read that corresponding omega n easily. Pictorially we can just read. That is graphical method of estimation omega n. We can do it. Okay, so you have to have a concentric circles imagined, or you can have a concentric circle already plotted. On such graphs, if you identify poles and zeros, very easy to read the corresponding omega n and the zeta value. We'll just see how to read the zeta value. So zeta value also, it is a very simple procedure here. You have to first identify poles and zeros on the S-plane. We have done it. There is a complex poles we have, complex conjugate poles we have. This can happen for the underdamped situation. So we have two poles here. You have to join this pole to the origin. Okay, this is what I call it as omega n. Okay, the length or the chord or the line what we have, we call it as the omega n value. Now you have to imagine an angle formed here. That is, this line is making some angle with the negative real axis. Negative real axis. That angle we call it as theta. Cos of that angle is what we call it as the damping ratio. Okay, cos of that angle what we call it as the damping ratio zeta. Okay, so what I can do, I can imagine I can imagine different zeta lines, and I can again imagine many zeta lines on the S-plane, so that the pole, whichever pole lies on any particular line, I can read the zeta value directly from the graph. Okay, so for the undamped system, you will be having zeta taking a value 0 to 90 degree, correct? For zeta 0 to 1, zeta 0 to 1, you will find that the angle changing from 0 to 90. Very simple. And for undamped system, zeta is 0, and because you can see that poles lies on the imaginary axis, so I can say that theta is equal to 90 degree, correct? So that is pole making an angle with the negative real axis. It is actually what we call it as theta. It is 90 degree, you can see. Okay, so for overdamped condition, overdamped and critically damped system, you have theta 0. You have theta 0. So zeta will be always greater than or equal to 0. Okay. So now what I do is I draw a line here. Okay. I'll draw a line. Okay. So this is having a fixed angle 45. So whatever poles lies on this line will be having the same zeta, that is cos of 45, which is 0.707. Okay. So what I did, I have taken many poles here, say 4 to 5 poles I can take it. So all the poles which lies on this line will be making the same angle with the negative real axis. So zeta has to be same. So I call this as a zeta line of 0.707 value, or a zeta line with an angle 45 degree, you can call it as. So whatever poles which lies on these line will be having a what we call same zeta value. Okay. So I'll just stop here. I'll continue with this in the next class. So we have learned, how to imagine a concentric omega n circle, omega n rings, and how to imagine a zeta line in the S plane. We will see pole zero mapping or pole zero plots. We will see, and let us try to read the omega n value and zeta value graphically in the next class. Okay. Thanks for the patience hearing.